Hi, I'm Robert Kawecki, and the subject of the presentation, as can be seen, is writing reliable applications. But before we actually get to see under the hood of the application, which we are going to be overviewing by example today, let's first wonder for a while why we are even talking about it. Well, most often it might seem that reliability is a pretty much solved problem, because as long as our database is persistent and durable, nothing can go really wrong, can it? I mean, when our changes have been persisted to the database, then they are there, aren't they? But what of the client? The client knows that the database has persisted their changes only if some kind of transport notifies the client. So we need some kind of acknowledgement that the changes that the user was interested in actually happened. And as we all know it too well, networks can and do fail. And the question is not if, but when. So how does our application behave when the network is unreliable? Well, that's about the topic of the presentation. The problem with networks is compounded by the fact that humans are notably bad at dealing with network failures. So they are liable to click a button multiple times just to see something happen. So I'm sure we've all seen multiple instances of, oh, sorry, double post. And that's a pretty awkward situation in such cases, but it's not nearly as bad as being billed for a transaction 3 times. So we should try our best not to duplicate those changes. And also, when integrating multiple systems via some external APIs, we need to ensure an even greater degree of reliability, because users are intelligent, or at least most of them, and they can react in an adaptive way to changing network conditions and to the input. But systems need a different kind of reliability, one that is rock solid and well-defined at all times. So we define reliability for the purpose of the presentation as trying really hard to do what the user wanted. So we employ different measures, different mechanisms that guarantee durability and execution of a given command. Failing that, we must fail in a predictable way, so our application cannot just do anything. A good example of that is databases which expose the ACID property, which means, among others, that only one of 2 possible end states is possible. So we need to write our application so that the end state after every action is well definable. We also should give the user complete insight as to what's actually happening with the application. So the application should behave in a predictable way to the user as well. And even though the title said Node.js application, is really a matter of connecting the two, the front end and the back end. And that's where the usual suspect lies. Our goals, therefore, when building reliable applications, are that the application does not lose any effects desired by the user. So their commands should be applied immediately or eventually, but they should be applied, and that's our primary goal. Also, when doing that, we must ensure that only that which the user requested is done. So no effects should get ever duplicated, especially in business applications which have more severe consequences than just a double post. And last but not least, we need to guarantee that our applications carry their feedback to the user in a timely, predictable way, so that the user knows at all times that what he's dealing with, what the application state is. Now, as I said before, this presentation is going to be an overview of an existing Node.js and client-side application. But what is that mythical being that we're talking of? It turns out that this presentation actually doubles as the application. So as I click this button, things are going to change a little. OK, here's our application. It's actually integrated into the presentation. This simulates, or actually is, a bidding application that allows the user to take place in some user-defined auctions. I have chosen a predefined auction to appear in the top bar. So as you can see, the auction has a title, has a current top bidder. It's much like popular auction portals, but smaller. And this application allows us to actually take part in the bids. So I'm going to explain how it works later, but for now, behold. As you can see, the state has been updated. Let's take it up to 7. And it still works. Isn't that amazing? Okay, so let's look under the hood. This application is unlike many others you've seen. It does not use REST for reasons that I'm going to describe in a minute, but it actually uses the very lean and simple JSON RPC 2.0 protocol carried over WebSocket. So we are actually connected right now, and you can actually see that up here, that the connection, that the socket transport is up. So you get a request-response protocol overlaid over WebSocket, and also the same stream, the same connection is reused for carrying events, so state updates back to the client. So the highest bid that you saw updated was not a result of the client's actions solely. It was actually generated based on events that were delivered to the client asynchronously in the background. And this is all powered by a Node.js backend, which is just a technicality, but in the end, I'm going to provide some links to the complete source code of this client, the accompanying server application, and some libraries that made this possible. Why RPC, though? It seems an unpopular choice these days, where we can choose between REST and its well-definable replace or update semantics. But it turns out that REST is not always the only choice. This is maybe sounding a bit like the devil's advocate, but actually, JSON RPC was chosen for this sample application for its behavior semantics. So while we click the bid button, the user actually requested that their offer be placed. So they chose an action and applied it. The button was an example of a task-based UI, where you do not edit resources, but you instead submit some commands, some concrete commands for the server to execute. So it's an actual action by the user that gets applied on the server. I could have chosen REST, but this auction app does not seem to be very data-driven. And in fact, it's the user intention to take place in an auction. It is not their intention to replace the auction or to edit its data. They actually want to commit financially to a living auction. So there are some cases, especially with business applications, that RPC is actually well explained. Now, the patch method is pretty much non-standardized, so that's also the reason I avoided representative state transfer, or REST, if you will, for this case. So we actually only send simple requests. Another advantage is the RPC's native pipelining support, and that means that we never get head-of-line blocking in our application. AJAX calls often will get blocked by the browser if there are too many at the time, and as you can see in this simple dump of the JSON RPC, those are whole messages. Those are the requests that we provide the method name to call and the parameters that should be passed to a server-side function, the ID that you can correlate by, and the protocol version. And then you get the result, the ID that you can correlate with, so you can get as many in different order as is required, so that eliminates head-of-line blocking completely, and also the header. So this protocol is actually very simple, and it's a good thing for performance that we are not bloating our link. I mean, this operation is so trivial that it surely doesn't require a full post or put. But let's go on to actual semantics. Now, we said that we want no effects lost while running the application. So let's see what happens if the application actually does encounter a problem. This scrollable section is a preview of all requests that took place from the beginning of the application's runtime. So as we can see, the action has been loaded, and the response was okay. Those are just placeholders for success and failure, respectively. So we've managed to place an offer, and it worked. And then we placed an offer, and it still worked somehow. So let's try that, but this time, let's kill our network for a bit. This button does not simulate anything. It actually turns the WebSocket connection to the server off. So we are going to be running offline for a second. Let's see. OK, we're choosing to bet the current offer to 750 euros, which is not going to work for a while. Let's see. There's a request, but obviously it cannot reach the server. Now let's re-enable this network connectivity. And the server has actually reloaded the get auction. This call, in the case of this application, also reinstates some event subscriptions. And then we've sent our place offer again, and this time it worked. So as you can see, the state has been updated. So it means that the backend actually received our update and applied it. So that's a very simple solution to a problem that is bound to that we are bound to encounter in any application. We just employ a simple retry strategy, which is nothing else than a JavaScript function that controls the execution of another function. So we just get a set timeout or a set interval until it just works. It's very simple, but as we've seen, it's very effective. While we are using the application, we should always be getting consistent feedback as to what's happening. Unfortunately, I did not implement any kind of button blur or other visual indicators, but it should probably be here, such as a loader or disabling the button for as long as the request is running. So that's another part that we should be concerned about. Although in this case, the user has the live preview of the application state. So, well, we can say that they had the feedback at all times. Okay, but when retrying such commands, we need to make sure that they are not going to break our application. So we really do not want the user taking part in the auction multiple times, and especially if it were a service that creates a new auction, we do not want multiple auctions. I mean, the user is selling a watch, but he's not selling 10 watches. So if all those were sold, then he would have a problem. So we want no effects to get duplicated, and that means we need to prevent multiple executions of the same thing. But first, we need to ensure that really it is the same thing. So we get services that accept some arguments. We need to make sure that they always produce the same output. So in other words, the new state of the application. So for instance, the new contents of the auction entity are only ever determined by the old state, the current state, and the user input. That also means that all relevant identifiers, so for instance, IDs of auctions that are being created, have to be client-generated, and this cannot be stressed enough. In most applications, you have the database generating sequential or random identifiers for your client, but if you want complete determinism, then this just has to go. Below is an example of some code that is taken straight from the auction entity, and it implements the duplication of commands. So we can, if we just bid for the same amount multiple times, then this is a guard clause that will exit if it encounters an offer that was already placed in the entity, so in the auction, by the same buyer and by the same amount. So it's a simple method to ensure that our application is idempotent, which means that it will not do the same thing multiple times. Now, the last part of the puzzle, but perhaps one of the most important, is timely propagation of events and updates back to the client. And this example application uses a form of reactive messaging, which means that the backend generates messages that the clients receive. The common way to accomplish this is publish subscribe. And as we have seen, the get auction call that we were issuing also instates a subscription to events. So this is actually demonstrated here. There's a database that I'm going to explain in a second. And then those events that actually look like this, auction offer placed, flow down to the client. So the client has started a subscription to some component, and the component keeps sending it those subscriptions. Of course, when we reconnect, we need to reinstate the subscription because the old connection, old socket went down. So that's why after each reconnection, we issue a get auction again with a live parameter. Now, there are several frameworks which work similarly to this. For instance, Meteor.js uses a similar technique. It polls or listens to the database's changes and propagates them to the client. But it does so in a completely different way. And here's why. Meteor.js just listens to changes on database objects, which are records, documents, or some members of a collection. But it does not name them like this. Auction offer placed is the actual event name that's sent from the event store to the client. This application uses event sourcing as its storage method, which means that the whole storage of the application is realized as a stream of events. There are no tables, there are no collections, there's just one huge tape that goes to infinity and carries events with it. So when we take place in an auction, when we place a bid, then that bid is actually expressed as an event, and that's the primary storage method. So this is the event store is our primary database, and it contains events only and can send them. So we have a client here who is actively listening for new events. This is much simpler than detecting the changes like Meteor.js does, because we do not have to interpret the changes. We do not need to do any guesswork as to what has actually happened. So let's say that an auction comes up as closed, so that its state in the database changes to closed in a traditional system. Why was it closed? What do we show the client? Of course, we could update the preview, but if we wanted to issue some kind of notification, we would need to know the reason. So these events provide us with the reason. So if we actually get a database full of only meaningful event names that are propagated to whatever consumers might need them, then we have an application that has not only reliability, but business meaning. This is not only a publish-subscribe method, it is also a very powerful event architecture, application architecture. And this event sourcing is a big thing. It's not new, but it's certainly underrepresented in the programming community. Let's look at how it actually works. The event store, as I said, contains the events. So when an entity actually wishes to persist some changes, it does not make any direct writes to the database. It just emits an event that says auction offer placed, which was exactly what happened when I clicked the bid button. Then the event store persists it and publishes it to something called a projection. The projection is an intermediate representation that holds the current state for us. So for instance, this preview that we are seeing here is not served from the event store. The client does not query the event store. Instead, it queries the projection, which is built in the background. And it always has the shape that is desirable by the client. So we could have multiple projections of the same thing. We could have multiple shapes that are especially suited for different client applications. This also means that we can scale independently, and that's part of what command query responsibility separation is for. We can multiply the projection, so we could have 100 projections that are serving only read requests, so get auctions or listing auctions. And we could, at the same time, we do not have to multiply the event store. So we get extreme scalability possibilities on the right side, on the main storage, and on the read side, which is the projection for the clients to use for getting their data. Also, the events actually capture the intent, the business intent, so they offer some insight as to what has actually happened. And now, this presentation does not help to explore event sourcing at its depth, although it's a very broad subject and one that needs much merit. I believe there actually has been a presentation at meet.js about event sourcing and CQRS a few years ago, or a year, I'm not sure, but this, if you only had to pick one big subject and to explore, I would recommend event sourcing. Now, I hope that you can see at least a bit of how this application works, this client-server architecture. That's the gist of how it operates. And if we're going to learn something from this whole experience, let's formulate it into 3 simple ideas: that writing applications that are predictable requires careful design at both the architectural, so messaging and API level, and at the code level. So for instance, the conditional that you saw that eliminates duplicates in the entity actually has to be there. It actually has to be part of the domain logic. So we are not doing it as an afterthought. We are designing our applications from the ground up to be reliable. Also, the style of the API matters. So we need to design the arguments, the parameters to our services or to remote methods so that they are compatible with our reliability requirements. And last, reliability is not a thing that is to be taken for granted. So we need to be thinking about it constantly to write good applications. As we've seen, it matters not just from the server side, but also from the client side, because, well, this reconnect up here that uses WebSockets is not going to happen on its own, unless, of course, we are using a library that guarantees it. And that's about it. This application/presentation is available from my GitHub repository. So there's 2 parts to it. There's a front-end and the back-end part that are both open source and accessible for you. So we can explore and just see what makes it tick. Those are very minimal implementations, and you can run those on your local machines just to see what makes them work. And the cornerstone of the presentation has been the WebSocket client published courtesy of Greatcare. We actually have a stand outside, so if you enjoyed the subject, you can just come up and talk to us about it. Plus, we are hiring at the moment, so this application is actually what we do. So a thing like this is currently running on production, serving customers. And you can also install the lot from NPM, because there are real packages that you can just npm install, and that's about it. Since we are a bit ahead of the time, and the time for questions is going to be in a minute, let's just have some fun with it, shall we? Okay, that's just my graphics drivers lagging. I don't know why, but the HDMI makes it just do weird things, so just please give it a moment for it to open a new window. Oh, that's it. And what we're going to do is duplicate this tab. Come on, Chrome. You can do it. Yeah, it's actually worse than internet lags. Okay, we are going to duplicate this tab. Oh, that worked. And we're going to put 2 of those guys side by side to see what real time is all about. Okay, this is not real time. I hope it won't invade on the question time. Come on, application.
Internet Explorer.
Yeah, I wish. Okay, I don't think we're gonna make it for some. Oh, we actually could. Okay, let's try it. Okay, I'm actually bidding now. So as I click this bid button, can you please watch the left section, this amount? Okay, let's do it. Just wait for it to settle. And the graphics. Okay, now we're doing it. Okay, this is, I'm not exactly sure why it's taking so long, probably the graphics still, but oh, I hoped for a more of, oh, okay, it's updated. Let's try it again without. Okay, that's it. If you want to see it in action, I will be with the laptop at our stand, so feel free to just come up and watch it in action without the graphical lags, hopefully. And yeah, now's the time for questions.
Okay, so if you build your application using this approach, this WebSocket approach, how do you take the first state? So is it REST or everything is going through WebSockets? And if so, what's the performance impact?
This example application that we've seen today actually runs only on WebSockets, so there are no HTTP connections whatsoever made to the backend system. I have not personally measured the impact on performance, but let me say that I have benchmarked a WebSocket the other day, a WebSocket server that used the Node cluster module, and I could, on this very laptop, I could push 3 gigabits per second of commands and replies. So the performance impact is, as you can see, very minor, and I think that it easily beats HTTP hands down.
Hi, you're using the JSON as the communication format, right? So you're exchanging entire JSON tree, because in some more complicated apps it's probably big. Have you considered that? JSON patch, for example.
Excuse me, what was protocol?
JSON patch. This is the patch exchange extension to JSON.
Oh, you mean the RESTful implementation of the patch method? Okay.
No, not the patch method in HTTP, but the JSON patch.
Now, to be honest, I have not considered it, but it's always an option. This example application is not meant to be a guideline. It's only supposed to show one way to do it. While the architecture section always holds true, you can mix and match protocols. So if you want to build such an application on any other protocol than JSON RPC, feel free to do it. Why not? The JSON RPC was a logical choice here because I encapsulated my domain logic as services that are remotely callable. So I did not want to deal with state transitions and generating events based on differences between the old and the new version, so on the patch input. But you could very well do it.
Okay, someone else? No questions?
Do you handle conflicts in your protocol somehow? Because the user may click sequentially some actions that are in conflict to each other. Okay, well, there's 2 cases. One case when the different writes do not conflict logically is pretty simple, because I assume you mean concurrency control, so avoiding writes at the same time. So the application does that by using optimistic concurrency control, which means that every transaction tries to write its own event into a certain slot, which is just a number that identifies it uniquely. And if the event fails to write it, because the database says the slot is taken, then we just retry. We reload the current state of the entity and retry the whole transaction, which is expressed as a JavaScript function. And when those are found to be incompatible with the current state, then it's a logic error to the user.
Okay, so thank you, and
Okay.
wait a second.
If you feel fascinated by this whole subject, feel free to come up to our booth. It's great core software, and we actually wrote those libs. So yeah, we know a thing or two about them. Thank you.